Bismillah ar-Rahman ar-Rahim. Matrices A and B are Hermitian and positive definite. We want to prove that the trace of matrix B can be expressed as the maximum over A of the trace of A log B minus A log A plus A. We can characterize the trace as this maximization problem. This variational characterization of the trace may look pointless. However, it can be a useful step in a big complicated proof. What is the logarithm of matrix A? Matrix A is Hermitian and positive definite. So matrix A is diagonalizable. Q is its unitary matrix of eigenvectors. Its inverse is Q Hermitian. And then we have here a diagonal matrix with the eigenvalues of A on the main diagonal. Because A is Hermitian, the eigenvalues are real valued. And because A is positive definite, then the eigenvalues are strictly positive. Here are the eigenvalues, lambda 1 of A, lambda 2 of A, all the way to lambda n of A. Log A is defined as follows. We have Q Hermitian, and then the diagonal matrix. On the main diagonal, we have the logarithms of those eigenvalues, log of lambda 1 of A, log of lambda 2 of A, all the way to log of lambda n of A. We assume that the eigenvalues are ordered. Lambda 1 is the maximum eigenvalue, lambda n is the minimum eigenvalue. Note that log A is Hermitian. If you take the Hermitian of this matrix, you get Q Hermitian, this is Q. Then you get the Hermitian of this matrix. Because the eigenvalues are strictly positive, then those logarithms are real valued. And the Hermitian of this diagonal matrix is simply itself. Then the Hermitian of Q is Q Hermitian. This is exactly the logarithm of A. The logarithm of A is a Hermitian matrix, but it is not necessarily positive semi-definite or positive definite. If lambda j is from 0 to 1, then the logarithm is negative, but it is a Hermitian matrix. To prove our variational characterization of the matrix trace, we will need to prove this inequality, that the trace of B minus A plus A log A minus A log B, this is non-negative. And to prove this result, we will need a widely known result about the trace of the product of two Hermitian matrices. This result here is not specific to positive definite or positive semi-definite matrices. The matrices just need to be Hermitian. The trace of the product is upper bounded and lower bounded by sums that involve the eigenvalues of A and the eigenvalues of B. Start by proving this very useful result, then we prove this inequality, and then we go back to the variational characterization. Before proving the lower and upper bounds on the trace of the product AB, let's remind ourselves of two very important facts. If A and B are Hermitian and positive semi-definite matrices, the eigenvalues of AB are non-negative. If A and B are Hermitian and positive semi-definite, then the eigenvalues of each one of them is non-negative. The eigenvalues of the product are also non-negative. Suppose that lambda is an eigenvalue of AB. The associated eigenvector is Q. We have A, B, Q is equal to lambda Q. Q is not equal to the all zero vector by definition. Eigenvectors are not the all zero vector. Multiply both sides of the equation from the left by Q Hermitian, B Hermitian. So that's Q Hermitian, B Hermitian is just B. A, B, Q is equal to lambda Q Hermitian, B, Q. We can rewrite this as BQ Hermitian A, and then we have BQ is equal to lambda and then Q Hermitian BQ. That's a quadratic form involving matrix A. That's a quadratic form involving matrix B. Both quadratic forms are non-negative because A and B are Hermitian and positive semi-definite matrices. Note that if Q Hermitian BQ is strictly positive, then we can divide by it, and lambda is the ratio of these two quadratic forms. Upstairs in the numerator, this quadratic form is non-negative, and by assumption in the denominator we have something that is strictly positive, so lambda is greater than or equal to 0, non-negative. What if Q Hermitian BQ is equal to 0? If this is 0, then also this is equal to 0. So Q Hermitian B A BQ is equal to 0. Let's take this matrix A and split it into A to the 1/2. A to the 1/2 BQ is equal to 0. A to the 1/2 is defined similar to the logarithm of A. If A is Q and then the diagonal matrix of eigenvalues and Q Hermitian, then A to the power 1/2 will have here square root of lambda 1 of A all the way to the square root of lambda n of A. A is a Hermitian positive semi-definite matrix. Those are non-negative real numbers. We don't have troubles with taking the square root. This is A to the 1/2 B Q all Hermitian. B is a Hermitian matrix like log A. A to the 1/2 is also a Hermitian matrix, and in this case it is positive semi-definite. When we take the square roots, those guys remain non-negative, and so A to the 1/2 is Hermitian and positive semi-definite. The logarithm of A is Hermitian, but it is not necessarily positive semi-definite unless all the eigenvalues are greater than or equal to 1. This here is A to the 1/2 BQ. So we have a vector Hermitian times a vector equal to 0. This is the L2 norm squared of the vector. Vector norms are defined such that the norm is 0 if and only if the vector itself is the all 0 vector. So A to the 1/2 BQ is 0 n by 1. Multiply both sides from the left by A to the 1/2. We get A BQ is equal to the all zero vector, which can be written as 0 times eigenvector Q. In this case here, lambda is equal to 0. So in both cases, lambda is non-negative. If A and B are Hermitian positive semi-definite matrices, the eigenvalues of AB are non-negative. If matrix A is Hermitian and positive semi-definite, its eigenvalues are equal to its singular values. Sigma of A, one of the singular values of matrix A, is the positive square root of lambda of A Hermitian A. A is a Hermitian matrix, so A Hermitian A is A squared. Lambda of A squared, an eigenvalue of A squared, is lambda of A squared. And then you take the square root, that's lambda of A. When A is Hermitian and positive semi-definite, its singular values are the same as its eigenvalues. We want now to establish bounds on the trace of AB. Our theorem is concerned with Hermitian matrices, but let's start by assuming that A and B are Hermitian and positive semi-definite. As we have seen, the eigenvalues are non-negative. The trace, which is the sum of the eigenvalues, is non-negative, and so the trace of AB is equal to the magnitude of trace AB. Now we apply Neumann trace inequality. So generally we have trace, and let's say that we have two matrices, C and D. They do not need to be square matrices. Their product must be square. So suppose that this is K by M, and this one should be M by K. The trace of CD, if we take the magnitude by the Neumann trace inequality, this is upper bounded by a sum that involves the singular values of those guys, sigma J of C, sigma J of D. And we use the same ordering. So sigma 1 of C is its maximum singular value, and sigma of rank C of C is its minimum positive singular value. The upper limit of summation, we can put here K or M or the minimum of the ranks of these two matrices. The convention is that sigma V of C is equal to 0 if V is strictly greater than the rank of C. This is a general inequality. In our case, because the matrices are Hermitian and positive semi-definite, then the singular values are the eigenvalues. So for Hermitian and positive semi-definite matrices, indeed, the trace of AB is upper bounded by a sum J from 1 to n, lambda J of A, lambda J of B. We have a sum of products. The upper bound is lambda 1 of A, lambda 1 of B. Those are the maximum eigenvalues of A and B respectively, plus lambda 2 of A, lambda 2 of B, and so forth. What if A and B are not positive semi-definite? So here is the trick. If A and B are just Hermitian, there exists gamma 1, that is a non-negative real number, and gamma 2, that is a non-negative real number, such that A plus gamma 1 times identity and B plus gamma 2 times identity, both those matrices are positive semi-definite. The idea is that when we add gamma 1 times identity to A, if the eigenvalues of A are lambda 1 of A all the way to lambda n of A, then the eigenvalues of A plus gamma 1 times identity, we just add gamma 1 to those eigenvalues. So the eigenvalues of this matrix here are lambda 1 of A plus gamma 1, lambda 2 of A plus gamma 1, all the way to lambda n of A plus gamma 1. Gamma 1 is added to all those eigenvalues. Gamma 1, if it's large enough, all those eigenvalues can be non-negative. For example, suppose that the minimum eigenvalue of A is minus 5. If you choose gamma 1 to be 6, that's it. All the eigenvalues of the matrix A plus gamma 1 times identity will be non-negative or even positive. We have proved our upper bound for Hermitian positive semi-definite matrices. So we can apply this upper bound not to A and B because they are just Hermitian, but we can apply our upper bound to A plus gamma 1 times identity, B plus gamma 2 times identity. In this case, the upper bound would be summation J from 1 to n, lambda J of 1 plus gamma 1 times identity, and then lambda J of B plus gamma 2 times identity. Let's focus on the left-hand side. We get 4 terms when we do the multiplication. We have AB, we have gamma 1 times B, we have gamma 2 times A, and then we have gamma 1, gamma 2 times identity. The trace is a linear operator, so the trace of the sum is the sum of traces. So we have trace of AB, we have gamma 2 the trace of A, gamma 1 the trace of B, and then gamma 1, gamma 2 the trace of identity, which is equal to n. On the right-hand side, the eigenvalues of A plus gamma 1 times identity, those are the eigenvalues of A plus gamma 1, and those are the eigenvalues of B plus gamma 2. If we multiply, we get the product of the eigenvalues. We get also gamma 1 lambda J of B, we get gamma 2 lambda J of A, and we get gamma 1 gamma 2, and then we sum. When we sum the eigenvalues of A, this is the trace of A. So we have a term here which is gamma 2 the trace of A, exactly like this term. And this will be gamma 1 the trace of B, exactly like this term. When we sum gamma 1 and gamma 2, that's a constant. We add it to itself n times, and so we get n gamma 1 gamma 2, which is this term here. So we have 4 terms on the left-hand side, 4 terms on the right-hand side. 3 terms are exactly the same on both sides. You can eliminate those terms, and we end up with the trace of AB less than of the sum J from 1 to n lambda J of A times lambda J of B. In other words, our upper bound is not restricted to positive semi-definite matrices. We just need A and B to be Hermitian matrices. To derive the lower bound, here is the trick. If matrix B is Hermitian matrix, and this is its eigenvalues, lambda 1 of B greater than or equal to lambda 2 of B all the way to lambda n of B, minus B is also a Hermitian matrix. the eigenvalues of minus b are minus lambda 1, minus lambda 2, minus lambda 3. And if we arrange these in a non-ascending order, then we have minus lambda n of b is greater than or equal to minus lambda n minus 1 of b. And the minimum eigenvalue of minus b is minus lambda 1 of b, is minus the maximum eigenvalue of b. We have an upper bound result. So let's apply this upper bound to the product of the Hermitian matrix A and Hermitian matrix minus b. So we have here minus trace of AB. On the other side, we have summation j from 1 to n, lambda j of A. Note that lambda 1 of A must be multiplied by the maximum eigenvalue of minus b. That's minus lambda n of b. Lambda 2 of A must be multiplied by the second largest eigenvalue of B. That's minus lambda n minus 1 of B. Generally, we have lambda j of A is multiplied by minus lambda n plus 1 minus j of B. So that lambda 1 of A is multiplied by minus lambda n of B. Lambda 2 of A is multiplied by minus lambda n minus 1 of B, and so forth. We can take this minus sign outside. Now we have an inequality, multiply both sides by minus 1, and that's it. We get that the trace of AB is lower bounded by this summation here. This is one very useful result regarding the trace of the product of two Hermitian matrices. We have an upper bound and a lower bound, both in terms of the eigenvalues of these matrices. Now we need to prove that the trace of b minus a plus a log a minus a log b is greater than or equal to 0. Trace is linear. This inequality is equivalent to showing that the trace of a log b minus a log a, as if we move these guys to the other side, so this is less than or equal to the trace of b minus a. Trace is linear. We can write this as trace of a log b minus trace of a log a. As usual, we have a is q, and then we have lambda 1 of a all the way to lambda n of a, and then q Hermitian, a log a is q, and then we have lambda 1 of a, q Hermitian, and log a is q, and then we have here log of lambda 1 of a all the way to log lambda n of a, q Hermitian. Q is a unitary matrix, q Hermitian q is identity, and then we can multiply the diagonal matrices. So a log a is a matrix that looks like this: q Hermitian. Here we have lambda 1 of a log lambda 1 of a, and then lambda 2 of a log lambda 2 of a, and so on. The trace of this matrix is the sum of its eigenvalues, and this is summation j from 1 to n lambda j of a log lambda j of a. Here we have two Hermitian matrices. A is Hermitian, and it is positive definite. Because we have here log of b and log of a, then we are taking the logarithms. We need the eigenvalues to be strictly positive. So a is Hermitian and positive definite. It is Hermitian. Log b is not necessarily positive definite, but it is Hermitian, and we can apply our upper bound. Trace of a times log b is upper bounded by the sum, in which we have here the product of lambda j of a, and then the jth eigenvalue of log b is log lambda j of b. Now combine these two sums. So we have summation j from 1 to n lambda j of a as a common factor, log lambda j of b minus log lambda j of a. This can be written as log lambda j of b divided by lambda j of a. Now we use the inequality that whenever we have a strictly positive alpha, log alpha is less than or equal to alpha minus 1, with equality if and only if alpha is equal to 1. In other words, we have this natural logarithm of lambda j of b lambda j of a. This is less than or equal to this ratio here, lambda j of b over lambda j of a minus 1. Multiplied by lambda j of a, so we get lambda j of b, and then we get lambda j of a. This sum is the trace of b. This sum is the trace of a. The trace is the sum of the eigenvalues. So indeed, the trace of a log b minus a log a is upper bounded by the trace of b minus a. We can join these guys here, and we obtain this inequality, the trace of b minus a plus a log a minus a log b. This must be non-negative, where a and b are Hermitian positive definite matrices. Finally, we want to provide an argument for this variational characterization. From the previous page, we have the trace of b minus a plus a log a minus a log b. This is greater than or equal to 0. We can just keep b here and move the others to the other side. So the trace of b is greater than or equal to the trace of, we have here a log b minus a log a plus a. Now take the maximum or the supremum of both sides over a. This side does not contain a. The maximum is just the trace of b. And the other side, we have the maximum with respect to matrix A. So matrix B is given, and we try to find the maximum value of this trace here by varying the Hermitian positive definite matrix A. So trace of b is greater than or equal to the maximum over a of this trace here. The maximum of this trace here is greater than or equal to the trace of this quantity a log b minus a log a plus a if we make a particular choice of a. So the maximum over a of this trace is greater than or equal to, let's choose A to be equal to B. B is a Hermitian positive definite matrix, so a feasible choice for matrix A is to set A equal to B. If you do this, you have a lower bound on the maximum. What if we put A equal to B? We will have trace of B log B minus B log B plus B. That's the trace of B. So this maximum is greater than or equal to the trace of B. Trace of B is greater than or equal to the maximum. Then the trace of B is indeed equal to the maximum over A of the trace of A log B minus A log A plus A.